right? And it's the curiosity. I still know that I was traveling from Nagpur to Shegaon, and in our car, we have a kid who was just 3.5 years. During the road from Nagpur to Shegaon, the girl asked so many questions. She was very curious about different trees. She was very curious about river. She was very curious about different cars, right? And she was keep on asking questions. That's a curiosity, right? And it's the curiosity that leads to thinking. We ask. You imagine. I still remember. I had one student, and when I started my teaching, she was of the first batch. And uh, last year she came and met me, and she told me that her son, who is a 5 years old, is continuously asking question, and she said that it's so irritating for her, and I'm now fed up answering her. I very calmly and patiently answer her that I wish this ability, this tendency of asking question remain alive even beyond age of 12, 13, 14. We have seen that as the age increases, because of inhibition, because of because of peer pressure, we stop asking questions, right? And slowly with age, this curiosity exponentially decreases. Maybe when you are now 18 years of age, first year or second year or final year, we hardly ask questions. We hardly explore. We merely follow what is taught in class, or maybe what is asked in previous 5 years question papers, right? We stop asking. We stop remaining anxious, and probably that has led to not thinking. It's the thinking, whether it is design thinking, whether it is innovative thinking. What is most important is thinking, right? There was a saying that I am dangerous because I think. The ability of thinking is extremely important, and each of us is blessed. It is the basic instinct to ask and question. Let's take some couple of examples, right? To explore is inherent. That we do. Let's take some examples what we do on a day-to-day basis. I will tell you a couple of examples. Right? I will tell you one simple example. When I used to come to LIT from Trimurti Nagar, we have to climb this Ambazari. From Ambazari, we used to come backside of Dharampet's college. Me and my friend, we both used to come by cycle, and invariably many times that time it was cycle only. Unlike now, now most of you must be having a bike or a two-wheeler. We used to come by cycle, and in cycle sometime there will be the carrier is making noise, right? Some or the other thing will happen because the cycle, I was using my elder sister's cycle. My elder sister is 5 years elder to me, so you can imagine how old that cycle was. Everything of the cycle used to make noise other than the bell, and finally I was never I mean I removed the bell, right? But when we confront with all these problems, we never succumb to the problem. We always try to make some kind of jugaad. Those who are residing in hostel life, you have to do a lot of jugaad. Even at home, if you find some water is leaking in the basin, right? You do not allow that leak to take place. You will do something. काही ना काही आपण करतो की जेणेकरून दरवाजाचा आवाज येत असेल. We will do something, right? So that's the ability of problem solving. We do not live with problem at the max, right? Now imagine, I always ask students that if you want to become a successful chemical engineer, be a cook. Because when you cook, you must have imagined, now all of us are at home, and during lockdown also, many have experimented with cooking. When you cook, you do a lot of experiments, right? You take an example. भाजी बनवलेली असते, कधी मीठ जास्त होऊन जातं, तिखट कमी होऊन जातं, काही ना काही होतं. Have you ever observed your mother, those who are cooking at home, they will take, they will go in the kitchen, they will do something, right? आता पहा, आता व्यवस्थित झालेली आहे भाजी, राईट? आपण खायला लागतो. दैनंदिन, these are all examples of day-to-day life. So, cooking gives you an opportunity. If you see, there is a channel, not only so, all this Marathi channel or Hindi channel in the afternoon, there is one show on cooking. Can you imagine the different types of, hardly there is a repetition. Reason is somebody will come, ते बोलवतात कोणाला तरी, एखादी बाई येते, एक वेगवेगळ्या प्रकारचे सँडविच करेल, कोणी हे करेल, ही भाजी करेल, वांग्याच्या नाना भाज्या. That's what the creativity is. I will tell you one simple story. Before I go forward, you must be knowing there is a variety of rice named as HMT. HMT is a variety from Vidarbha, very famous variety. And the one who has invented that variety, his name, I have forgotten his first name, his second name is Khobragade. One oldie, maybe in his late 50s, early 60s. And a man who had gone to any professional college, right? Maybe have done some schooling. This man has invented this variety HMT. Now the question was, from where this word HMT has come? This word HMT come because when he has come up with this new variety of rice with some specific qualities, somebody asked him, अरे याचं काहीतरी नाव ठेवावं लागेल, आपण नवीन प्रकारचा तांदूळ तयार केलेला आहे, नवीन धान आलंय आपल्याकडे. तर त्यांच्या हातामध्ये HMTचं घड्याळ होतं, तर ते म्हणजे ठीक आहे, आपण याचं नाव HMT ठेवून देऊ. सांगायचा उद्देश हा, की अशी व्यक्ती की जी प्रोफेशनल कॉलेजमध्ये गेलेली नाहीये, कोणत्या तरी खेड्यात राहते, and he has come up with a totally new variety, and now this variety is very popular. You can ask, if you go to any grocery shop, you can find out this HMT variety of rice. The question is that we don't require any professional degree, we do not require any age, we do not require any background. What we require is curiosity, and that curiosity leading to asking question, that curiosity leading to do something which is creative, right? Now I have given you a couple of examples. You just see, take an example, these are all day-to-day life examples. I want to watch a movie. Now there is one series going on The Scam, 1992, right? Harshad Mehta. You people may not be knowing, but the faculties who are attending, when I was in class 9, 10, when the Harshad Mehta episode took place. But before watching that, I searched for a review. कोणी काय म्हटलेलं आहे, कुठे काय लिहून आलेलं आहे, right? We do some kind of survey. Now from Amazon वरती तो ब्लॅक फ्रायडे सुरू होतो, we ask की कोणता डील आहे, काय आहे. That's a survey. That's the kind of a literature survey we do. If now in the lockdown we are not going to go outside, when you plan to go for outskirt, कुठे ट्रिपला जर जायचं असेल, we will ask, याच्या आधी कोण गेलं होतं, तिथे चांगलं हॉटेल कोणतं आहे, तिथे गेल्यानंतर काय करायचं, तिथे किती खर्च येईल. So that's the planning that so obviously we do, right? And that's a part of our life, that's a part of our design thinking, right? Now I will give you another example is, you want to travel, maybe in the month of December, तुम्ही पुढच्या महिन्यामध्ये तुम्हाला नागपूरहून दिल्लीला जायचंय, तिथून हैदराबादला जायचंय, चेन्नईहून पुन्हा नागपूरला यायचंय. So I have a travel plan from Nagpur to Delhi to Hyderabad to Chennai to Nagpur, right? 8-10 दिवस तुम्हाला जायचंय, प्रवास करायचा. And यू हॅव टू डू अ व्हेरी सिम्पल टास्क दॅट आपल्याला प्रवासासाठीची बॅग भरायची. जेव्हा मला प्रवासासाठी बॅग भरायची आहे, सो व्हॉट आर ऑल द थिंग दॅट वी टेक इन टू अकाउंट. आपल्याला एक लगेज घेऊन जावं लागेल, जास्त वजन नसायला हवंय. सो वी हॅव नाव फिक्स दॅट आय वॉन्ट टू कॅरी वन लगेज बॅग. Then what I will do, I will check the weather. The weather in Delhi, it's cold. So I need to have sweater. But then I have to go to Chennai also, right? Where it's not cold. Hyderabad, it's just like Nagpur, the weather conditions. So taking into account weather condition, we will take clothes. Taking into account what we want to attend, we will take necessary पुस्तकं घेऊ, नोटबुक घेऊ, लॅपटॉप घेऊन जायचा की नाही याचा विचार. राईट, दिस इज सो यू डू इट. तुम्हाला 2-3 मित्रांनी ठरवलं की आपल्याला कुठेतरी फिरायला जायचंय सुट्ट्यांमध्ये, पण बॅग जी भरतो, आपण जे प्लॅनिंग करतो, तिकीट बुक करतो, राहण्याची व्यवस्था करतो, परत येण्याची व्यवस्था करतो, दॅट्स ऑल kind of a thinking in a very organized way. It is nothing but a design thinking. We follow, and those are, I think, those are these steps. आपण पहिल्यांदा बघू, जायची गरज आहे का, खरोखर नाही गेलं तर काही फरक पडतोय का, राईट. So these are the steps of design thinking. Before that, I will talk about this in detail. Right? So I cover the first part, that innovation, creativity, doing experiment, exploration is something that you and me are blessed with, right? We do on almost a daily basis. Only thing is that we do not know what we are doing can be considered as research, right? Now the look at this thing. This is a very important diagram. It says that the 20 reasons of failure of startups. And the first and the foremost thing is need identification. No market need. खूपदा मुलांना आपण पाहतो की आमच्याकडे मी बऱ्याच मुलांशी जेव्हा इंटरॅक्ट करतो, स्टुडंट कम अप विथ आयडियाज, student come up with some startup ideas, right? And even this Institute Innovation Council, it encourages in stages ideation, problem ideation करायचंय, prototype तयार करायचंय, वगैरे वगैरे, right? The most important thing, you look at this, these are about startup. This is not, I mean, this is not the initial stage. This is where you have established startups. It says that the proper identification of a need is the most important. It's the most important thing. Whether you tomorrow become a research scholar, or now if you are in search of a project, if you want to do project in your third year and a final year, you need to identify a right problem. And identification of a right problem, you imagine 42%, close to 50, चुकीचा प्रॉब्लेम आपण सॉल्व्ह केलेला आहे, किंवा चुकीचा प्रॉब्लेम आयडेंटिफाय केलेला आहे, किंवा योग्य प्रॉब्लेम आयडेंटिफाय केलेला आहे. दॅट मेक्स हेल लॉट ऑफ डिफरन्स, राईट. माय टोटल फोकस इज नाउ ऑन दिस प्रॉब्लेम आयडेंटिफिकेशन, नीड आयडेंटिफिकेशन, राईट. देयर इज अ लिमिटेशन की जे मी आता मी तुम्हाला एक साधा प्रश्न विचार. प्रश्न असा आहे, एक गाव आहे, त्या गावामध्ये इलेक्ट्रिसिटी नाही आहे, जुनं गाव आहे, रिमोट गाव आहे, पण गावामध्ये लोकांजवळ मोबाईल फोन आहेत. नाव and of course we will assume that they need to they don't have this smartphone. They have typical old version of phones which require to be recharged once in a day, right? गावात लोकांना जिथे वीज नाहीये तिथे त्यांना मोबाईल रिचार्ज करायचा आहे. Can you tell me if with this as a problem statement, We want to recharge mobile on a daily basis. What could be the solution for this? And mind well, everybody has mobile, right? And टॉवर आहे गावात, दुसऱ्या गावात टॉवर आहे, तिथे इथे कव्हरेज येतो, राईट? पण गावामध्ये वीज नाहीये. हाऊ कॅन वी सॉल्व दिस प्रॉब्लेम? And there is a problem, right? So there is a problem now. I would expect if somebody can answer this. And don't worry, there is nothing called right answer or answer.
We can use solar panel, sir.
And one answer is one can use solar panel. Okay, what else? This is one of the solutions. Any other solution probable? Student can write private chat also, don't worry. Yeah, that is true. Basic solution is to provide electricity, but there is no electricity. Yeah, somebody can use even wind energy, right?
तर आपण जनरेटर यूज करू शकतो.
ना जनरेटर यूज करू शकतो, डिझेल वाला जनरेटर यूज करू शकतो. ठीक आहे. अजून we can have other renewable sources. Yeah, we can have different renewable sources, right? जनरेटर राहू शकेल, डिझेलचं जनरेटर राहू शकतं, गावामध्ये असतात लोकांकडे. So these could be different solutions. And mind well, there is nothing called a right answer or wrong answer. So what important is that we have come up with a solution. Then we need to go back and we need to validate the solution. I will tell you what actually is happening in that village. त्या गावात लोक काय करतात, एक कोणी तरुण आहे ज्यांना मोबाईल चार्ज करायचा, त्यांचे मोबाईल तो सकाळी 8 वाजता गोळा करतो आणि शेजारचं गाव की जिथे टॉवर आहे हा तिथे जातो, मोबाईल चार्ज करतो आणि घेऊन येतो. चार्जिंगचे 5 रुपये 10 रुपये घेतो, राईट? That's a solution which is existing. मग याचा अर्थ बाकीच्या गोष्टी चूक आहेत का? नाही. याचा अर्थ अरे बाबा पॉवर बँक साठी सुद्धा चार्जिंग तर कुठे करावं लागेल, राईट? That is what the stakeholder interaction. We will come up with the solution. एक खूपच सोपी आपण केस घेतली, मग आपण बघितलं ज्या पद्धतीने आपण विचार केला. या ऑनलाईन मध्ये हे दिस इज अ लिमिटेशन, अदरवाइज वी इन क्लास वी वुड हॅव डन दॅट. आपण विचार केला की रिन्युएबल वेगवेगळ्या सोर्सेस आहेत. इलेक्ट्रिसिटी नसली तरी सनलाईट तर आहे, वन कॅन यूज सोलर, वन कॅन यूज विंड, सो वी कॅन हॅव डिफरंट रिन्युएबल एनर्जीज, राईट? नाउ व्हॉट वी हॅव टू डू इज we need to go back to those who are suffering with the problems. You need to ask them, बाबा आम्ही तुमच्या ह्या प्रॉब्लेमसाठी आम्ही हे सोल्युशन घेऊन आलोय. What do you think about it? That is what the validation is. ते म्हणतील बाबा आम्हाला तर ठीक आहे, सोलर पॅनल वगैरे मागच्या वेळेला लावले होते सोलर पॅनल, चोरून गेले. विंड पॉवर इतका खर्च कोण करेल, आम्हाला पैसे कोण देईल? शेतात आहे तो घेऊन जातो मोबाईल, सकाळी 8 वाजता नेतो, आम्हाला काही रोज जावं लागत नाही, 2 दिवसाआड जावं लागतं, कधी 1 दिवसात आम्हाला मोबाईल चार्ज करायचा असतो, आम्ही 5 रुपये देतो आणि चार्जिंग करून घेतो, राईट? नाउ दॅट्स वेअर the most important thing when I am taking this course of innovative design for almost last 5 years, I will talk about that course also. What I realize is that the most important thing is immersion. The meaning of immersion is ज्यांचा प्रॉब्लेम आहे, can I feel the pain? Can I be empathetic towards the problem? Therefore, the need टू ॲड्रेस अँड नीड व्हॅलिडेशन. नीड टू ॲड्रेस आपण पाहिलंय की मला मोबाईल चार्ज करायचा आहे. तर मग तो खरोखरच प्रॉब्लेम आहे का? आपल्याला दिसेल नाही, खरंच गावामधल्या 15 लोकांजवळ तरी मोबाईल आहे, त्यांना चार्जिंग करणं आवश्यक आहे. So there is a need. Charging a mobile is a need that we need to address, right? Therefore, it says that everything starts with empathy. Empathy म्हणजे संवेदनशीलता. आणि एक एक त्याच्यातनं एक म्हण निघते, संवेदनशीलता से सृजनशीलता. So empathy leads to creativity because we are feeling the pain. Imagine करा, तुम्ही आणि मी त्या गावामध्ये काही कामासाठी 10-15 दिवस राहायला गेलो. आपल्याला तर मोबाईल शिवाय राहू शकत नाही. सध्या तर नवीन उपवास आहे. लोक आता एकादशी झाली, नवीन प्रकारचा उपवास सुरू झालेला आहे की व्हायला पाहिजे की 1 दिवस मोबाईल शिवाय. तो खरा उपवास आहे. 1 दिवस व्हॉट्सअप शिवाय, 1 दिवस फेसबुक शिवाय. Now imagine you and me are wanting to stay in that village for say 10 days or 15 days, maybe 1 week. आपण आपल्याला जेव्हा त्या परिस्थितीत स्वतःला ठेवू, त्यानंतरच आपण समजू शकतो की नेमका प्रॉब्लेम काय. म्हणून डिझाईन थिंकिंग मध्ये त्याला म्हणतात इमर्जन. आणि इमर्जन आणि प्रॉब्लेम आयडेंटिफिकेशन सगळ्यात महत्वाचा भाग आहे. प्रॉब्लेम आयडेंटिफाय केल्यानंतर मला वाटतो की हा प्रॉब्लेम आहे, पण तो खरोखरच प्रॉब्लेम आहे का, तिथे जाऊन त्या लोकांना विचारणं, दॅट इज कॉल्ड स्टेक होल्डर एंगेजमेंट. सो आय नीड टू अंडरस्टँड. सो व्हॉट इज स्टेक होल्डर? स्टेक होल्डर म्हणजे ऑल दोज हू आर रिलेटेड टू दॅट. आता आपण ह्या केसमध्ये आपण ती पॅडी स्ट्रॉची सुरुवातीला जी सांगितली ती केस स्टडी मी तुम्हाला सांगणार आहे. मी ती याच्या आधारावरती एक्सप्लेन करेल थोड्या वेळाला. सो दिस इज प्रॉब्लेम आयडेंटिफिकेशन. I talk about this. I will tell you the case that we have faced and a real story. The story is about this paddy straw, right? And with the help of that, we will try to understand these steps, then problem identification and solution, right? Instead of telling you only theory part, we will try to understand this thing with the actual example. आपल्याला माहिती आहे की गेल्या 3 वर्षापासून, त्याच्याहून आधी पण असेल, पण मोस्टली फॉर लास्ट 3 years the smog or the pollution in Delhi, in North India, has become a national, international issue. Every time during Diwali, somebody will go to Supreme Court, some government will tell, Delhi government will tell की आता या दिवाळीमध्ये फटाके फोडू नका कारण खूप पोल्युशन आहे वगैरे वगैरे. आणि त्याच्यामुळे ही गोष्ट न्यूजपेपरमध्ये यायला लागली. देन द विजिबिलिटी इन डेली वॉज सो पुअर की तुम्हाला अर्धा किलोमीटरच्या जास्त दिसत नाहीये. विमानं लेट व्हायला लागली, ट्रेन लेट व्हायला लागल्या. द प्रॉब्लेम हॅज एम्प्लिफाईड लाईक एनिथिंग. मग तिथे सापडलं की हरियाणा आहे, पंजाब आहे, उत्तर युपी आहे, तिथे लोक पॅडी स्ट्रॉ जाळतात. ज्या लोकांना शेतीचं बॅकग्राऊंड आहे त्यांना माहिती असेल की जे धान असतं पॅडी, सो वन्स यू हार्वेस्ट पॅडी, what is left over is the straw, right? And we have this is rice is here in kharif. Now rice and wheat is in Rabi. Typically in Punjab and Haryana and West UP, they have the wheat and rice cycle. म्हणजे ते खरीप मध्ये धान लावतात आणि रब्बी मध्ये गहू लावतात. द टाइम गॅप बिटवीन दीज टू इज जस्ट 3 weeks. साधारणतः ऑक्टोबरच्या मध्ये किंवा ऑक्टोबरच्या 3ऱ्या आठवड्यामध्ये धान वगैरे काढलं जातं आणि नोव्हेंबरच्या मध्ये 3 आठवड्यानंतर गव्हाची पेरणी होते, राईट. सो द टाइम गॅप लेफ्ट इज व्हेरी स्मॉल. So generally, to make your farm ready for the next crop, what the farmers conventionally used to do is they used to fire the forest, they fire the farm, and that used to because of its open combustion, you will find suspended particulate matters, and those suspended particulate matters with the wind used to come towards Delhi, right? And there is this problem. So the problem is there. Problem exists करतो. We don't need to search for a problem. There is a need. There is a need that we want to find out alternative to stubble burning. This is called stubble. Right? Then there are commissions. There was a task force by Niti Aayog. There is a task force by Agriculture Ministry. Prime Minister Office is also overseeing all these developments. It means that there is a problem, right? It's not a small problem. It's because the capital of the nation, the NCR, National Capital Region, is badly affected. So the number of people affected geographically, we can find out, it is badly affecting economy. Reason I will tell you. Last year, when I visited Ghaziabad in the month of November, 15 days, all manufacturing unit and all construction activities were stopped because they found that the construction activities also contribute to pollution badly. And manufacturing units are closed. मी सांगितलं की 10-15 दिवस कोणतेही मॅन्युफॅक्चरिंग होणार नाही, कोणत्याही चिमणीमधनं काही इमिशन येणार नाही. It affects environment, right? And from government point of view, politically, that was a priority, right? So when it comes to working on alternative to stubble burning, it complies most of the parameters. So the solution to this problem is very vital. If you look at this, yes, there is a need. What is the need? Need is to find out alternative to stubble burning. Have we validated the need? Yes, we have validated the need because it's available in media. We could interact with the people who are staying there. We have friends in Delhi. They are telling us we are traveling to Delhi. We found, yes, it's a problem. Right? Now, once we are very sure that there is a need and the need has been validated, then let us find out हे का आता कोणत्या कोणत्या पद्धती आहेत बाबा, आपण हाऊ कॅन वी address this thing? What are all the existing methods of solving this problem? Right? When we want to explore the existing method, we found that there are different methods. Methods are like people are using, तुम्ही पाहिलं असेल मध्यंतरी लोकांनी सांगितलं बायो सीएनजी. So make use of bio CNG. Let me take you there. Those are the things which are bio CNG from paddy straw, right? India's first one to convert paddy straw into biogas near Delhi. हे एक सोल्युशन आलं लोकांकडनं. बरं, दुसरं सोल्युशन आलं की पॅडी स्ट्रॉ वगैरे जे आहेत, मेक अ ब्रिकेट आउट ऑफ दिस. सो बायो मास ब्रिकेट फ्रॉम पॅडी, राईट? बायोमास ब्रिकेट म्हणजे हे ज्या पॅडी स्ट्रॉ आहेत त्या पॅडी स्ट्रॉला श्रेड करा. आफ्टर श्रेडिंग you convert it into bricks. I will show you images if we can. अशा पद्धतीने images तयार. It's just like a brick. There are two things. One is pallet and another is brick. Pallets are small. These are pallets. These are pallets, right? And these are, but if you consider a larger version in the sense that close to 6 inch to 8 inch diameter and 1 feet length, right? Those are your typically briquettes. So convert it into biomass briquette and use it. Second solution. And all this. So what we did is we did this. We try to look for the existing method of addressing the need. We look for that. Then we try to understand that why farmers are burning. What's the need of? Now you will find traditionally, it's a traditional practice की राख जी असते, राख ही शेतामध्ये पसरवली जाते. It's a traditional practice, right? So we come out with couple of methods. Bio-CNG झालं, your paddy straws, briquette झालं. We come up another solution, that is composting. Then we found out that they're very controlled combustion. In the controlled combustion means they are doing pyrolysis. त्याचं ऑइल निघतं आहे, जो बायोचार येतोय, बायोचार वापरला जातोय. So these are the existing methods, right? Then the question is, what should we take forward? जर काही existing methods आहेत, पण ते implement का नाही होते? किंवा ते implement होण्यामध्ये challenges काय आहेत? So we need to understand the existing solutions. Then we need to find out the gaps. की हो, याच्यामध्ये आपण काही अजून सुधारणा करायची गरज आहे का? लोक वापरत का नाही आहेत? याने काय होईल? याच्यात काही इव्हेंट करू शकतोय का? Right? Then what is found is that when it comes to bio-CNG, for bio-CNG, government has asked NTPC की तुम्ही लोकांनी पॅडी स्ट्रॉ घ्या, हे करा, ते करा. The paddy is extremely lightweight. पॅडी स्ट्रॉ समजायचं असेल तर पहिल्यांदा पॅडी स्ट्रॉ समजा काय. दिस इज पॅडी स्ट्रॉ. तणस जे असतं ना, तणस, आपण आंबे विकत घेतो, संत्री विकत घेतो, द्राक्ष विकत घेतो, ते तणस जे पॅकिंगला वापरलं जातं, दॅट इज पॅडी स्ट्रॉ, राईट? Now this paddy straw is extremely lightweight. Transportation of paddy straw, so since it's low density material, because of the low density, you will carry large volume, but the weight of that will be extremely less, which is not. So transportation cost is extremely high. But since the government is giving subsidy, government has asking this to happen, people are transporting it, right? Not only so, when it comes to transportation, one, we are transporting light material. Second, the transportation itself add to emission, itself add to carbon emission, right? But that's one of the solutions. But we found out, याच्यामध्ये हा प्रॉब्लेम आहे. दूसरा प्रॉब्लेम आहे, to have anaerobic digestion of paddy, the initial investment is extremely high. That is another issue. Third most important thing what has been identified by Niti Aayog and Ministry of Agriculture, that जे मटेरियल आहे, पॅडी आहे, त्याने ड्युरिंग इट्स ग्रोथ फेज जेव्हा झाड वाढलं, there are two things happen. With the help of photosynthesis, they form the organic part of the plant. But the inorganic part of the plant has taken from the soil, right? So the plant which has organic part and the inorganic part, the organic part is your can be burned out. The inorganic part, which is ash, is taken from the soil itself. So these task force are telling that one should त्याला एक शब्द वापरला त्यांनी, replenish. One should replenish the soil with the micronutrients and the nutrients, because the inorganic components which the soil has taken during its growth phase, if you are taking the paddy straw away from the agricultural land, you are depleting the nutrients. So ideally, to make it circular, it's ideal that the paddy should go back to the soil itself, right? There lies the answer for use of ashes in agriculture. Ash is used to be sprayed. The reason is ash contains inorganic compounds, it contains potash, it doesn't contain nitrogen, but it contains potash, it contains phosphorus, it contains zinc, right? It contains silica, magnesium, sodium, calcium, in some cases alumina also. So you take that, send back those material to the soil. See, all these are the indicators for finding me a solution. मला काय करायचंय, मला असं करायचंय की मला पॅडी शेतातून न्यायची नाहीये. एक दुसरं मला असं सोल्युशन बघायचंय की ती पॅडी मला शेतातच वापरायची. बरं ठीक आहे. मग त्याच्याने सोल्युशन्स कोणते आले की मला शेतातल्या शेतातच सगळ्या गोष्टी करायच्या. सो दे कॉल इट ॲज ऑन फार्म पोस्ट हार्वेस्ट सॉलिड मॅनेजमेंट, राईट? So I need to manage solid on the farm itself. With this, these are called constraints. When it comes to design thinking, these are my constraints. Okay, then we found out की मग चला ठीक आहे, असं जर करायचं आहे तर आपण कंपोस्ट करावं. कंपोस्ट इज अनदर वे. कंपोस्टने बरं, मग कंपोस्ट कसं करायचं? बिकॉज कंपोस्ट हॅज टू बी डन ऑन फार्म. फाईन. ऑन फॉर्म जर मी केलं, मी माझ्या ते मटेरियल पुन्हा सॉइल मध्ये वापरेन. सो आय एम सॉल्विंग अ प्रॉब्लेम ऑफ नॉट ट्रान्सपोर्टिंग द मटेरियल अवे. ऍट द सेम टाइम आय एम टेकिंग द मटेरियल बॅक टू द सॉइल. सो आय एम रिप्लेनिशिंग द सॉइल. बरं, मग आता हे कंपोस्ट होईल का? लिटरेचर शोधलं. जेव्हा लिटरेचर शोधलं, देर इज समथिंग कॉल्ड कार्बन टू नायट्रोजन रेशो. अॅनरोबिक डायजेशन वगैरे तुम्ही कदाचित अंडर ग्रॅज्युएटला नाहीये म्हणा हे सगळं. C/N रेशो, दॅट इज कार्बन टू नायट्रोजन रेशो. ठीक आहे. दिस इज अ व्हेरी व्हेरी इम्पॉर्टंट रेशो फॉर मेकिंग मटेरियल टू कंपोस्ट. What literature told me that there is this Punjab Agriculture University. Punjab Agriculture University is working on making compost. See, आता काय चाललंय, now on which phase are we? आता आपण सोल्युशन फाइंड करतो. एक्झिस्टिंग मेथड्स फाइंड केल्या, आता आपण सोल्युशन फाइंड करतो. ठीक आहे. आपल्याला सोल्युशन असं पाहिजे आहे की ऑन फार्म होईल, शेतातली गोष्ट शेतात वापरली गेली पाहिजे, शेतकऱ्याला ती करता यायला पाहिजे. देर शुड नॉट बी ऍडिशनल इनिशियल कॉस्ट. मशीन बाकीच्या गोष्टी असल्या तर बरं होईल, राईट? सो विथ दिस कन्स्ट्रेंट, द प्रोबेबल सोल्युशन व्हॉट इज फाउंड इज कंपोस्टिंग. वन्स अगेन लेट्स फाइंड आउट व्हॉट आर ऑल द मेथड्स ऑफ कंपोस्टिंग. लिटरेचर मध्ये काय दिलंय कंपोस्ट बद्दल, किती वेळामध्ये होतं, काय वेळ लागतो. ठीक आहे. तुम्ही ऍडव्हर्टाइजमेंट पाहिली असेल स्वच्छ भारतच्या वेळेला, यू विल सी दॅट स्वच्छ भारत सर्वेक्षण, Nagpur city also participate. All these cities are participating, and the one of the during their campaign, during their advertisement, they say that तुमच्या इथला ऑर्गॅनिक कचराचं कंपोस्टिंग होतं का? होत असेल तर इतके मार्क, होत नसेल तर इतके मार्क. सो कंपोस्टिंग ऑफ ऑर्गॅनिक मटेरियल इज अ नोन फॅक्ट. देयर इज नथिंग इनोव्हेटिव्ह इन दॅट. Vermicompost is a very known thing. Those who have garden at home, right, you will find that तुमच्याकडचा माळी किंवा तुम्ही लोक, you are using this compost, right? Now when we are using this compost, mostly the compost is made from leaves. It's made from green material. It is made from kitchen waste. And all this material, the carbon to nitrogen ratio for this material is somewhere close to 20, close to 25. But when it comes to material like paddy straw, which is extremely dry and the nitrogen content is less than 3%, the carbon to nitrogen ratio is close to 55. you will find that if you have paddy straw, the paddy, that's the reason paddy straw is used as a packing material, because it doesn't degrade, it doesn't decompose. When the example that I give you, that paddy straw is used as a packing material in your mangoes, or in case of your grapes, the packing material remains as it, the paddy remains as it is over a period of time. It doesn't degrade. The reason is the carbon to nitrogen ratio and the nitrogen content in paddy is extremely less, and that is the biggest challenge. When we search for the literature, we found that there are scanty work done on the decomposition, biodegradation of rice straw, right? The time that is required for digestion is close to 4 to 6 months. Somewhere the minimum time period that we found is 90 days, that is 30 days, right? So from 1 acre of paddy land, paddy harvested land, 2 tons of paddy straw is generated, right? Now, if you require 4 months or 6 months for digestion, that is not advisable. I cannot afford to stay for 4 months or 6 months for composting to take place, right? So what we need to do is we need to find a method such that we can reduce the time. And there where we actually found out the area on which we need to work, that we need to reduce the time of degradation. Fine, we want to do composting, right? We will do it on farm. But the real challenge is that, can I do it in minimum time, right? And there where the experiment started. So we have done the 4 stages. To do these first 4 things, we spent close to 6 months. A lot of immersion, a lot of involvement, interaction with farmers, interaction with people in North India. We actually tried to understand the problem. And then we pinpointed our problem, that we want to reduce, we want to rather fasten, we need to accelerate the digestion of a material whose carbon to nitrogen ratio is 50 to 55, and we want to do it in as minimum time as possible, right? Now we are now able to do it in just 21 days. It is the fastest ever digestion which is possible, which we have shown in the initial video. Now we found that those who know little bit of anaerobic digestion, there are 4 stages of digestion: hydrolysis, acidogenesis, acidogenesis, and then finally methanogenesis, right? Here, what we found is that we have come up with a culture. One of my student, who she is PhD in biotechnology, we come up with a culture, right? And now I will tell you the story of solution and validation of solution. So many iterations. For last 1 year, we have done so many iterations. Around 15th of August, the technology is ready. Now, what are all the steps through which we went? Very simple problem, apparently very simple, but the kind of impact it's going to have is humongous. Now look at the things. We initially, what we did is we come up with a culture, and we took paddy. I'm telling you how experiments were performed. And while doing the experiment, where we need to actually interact with the stakeholders, आणि कशा पद्धतीने सोल्युशन मध्ये चेंजेस करण्याची गरज आहे. So our first model was, आम्ही अर्धा किलो पॅडी घेतली, राईट? पॅडी आम्ही मागवली तिथली पॅडी, बिकॉज दॅट पॅडी कंटेंट सिलिका. आपल्या नागपूरच्या आजूबाजूला भंडारा, गडचिरोली या भागामध्ये सुद्धा पॅडी होते, पण त्यात सिलिका नसतं, फार कमी सिलिका आहे. तिथे फार जास्त प्रमाणात सिलिका आहे. सो वी ब्रॉट दॅट पॅडी, shredded paddy. Once we brought that shredded paddy, initially what we found is that we need to go for 2 stages of anaerobic digestion. एकदा मटेरियल घ्या, कल्चर टाका, त्याला पूर्ण बंद करा anaerobically, राईट. मटेरियल बाहेर काढा, पुन्हा त्याच्यामध्ये कल्चर टाका, पुन्हा ते बंद करा. नाउ देअर वेअर कंडिशन्स. दोन इंजिनिअरिंग इश्यूज आहेत. The first engineering issue was the amount of water required, and second is the volume of the reactor. Right? Those people were telling that आमच्याकडे पाण्याचं कमतरता आहे, आम्हाला अशी प्रोसेस पाहिजे आहे की पाणी कमी लागेल. बायो सीएनजी आपण जे पाहिलं होतं त्याच्यामध्ये सॉलिड टू लिक्विड रेशो 1:20. So if you take 1 kg of water, 1 kg of paddy, you require 20 kg of water. Right? Of course, ते पाणी पुन्हा रिसायकल केलं जाणार आहे. Here, they said that we want less water, as minimum water as possible. And second, that if you reduce the amount of water, the volume of the reactor that will be required will also reduce. Right? So volume reduce झाला, costing reduce झाली, equipment ची costing reduce होईल, equipment ची sizing reduce होईल, सगळ्या गोष्टी reduce होतील. When it comes to density of paddy is 40 kg per meter cube, density of water is 1000 kg per meter cube. Right? So if you are using so much of water, foundation, material of construction, thickness of material, that all will change. Right? So this is the feedback what the end user gave us, and based on that we made our process. मग आम्ही विचार केला, there is something called solid state fermentation. In case of a solid state fermentation, solid to liquid ratio should be close to 1:1. But this idea come when we got the feedback. I'm talking about now solution and validation of solution, interaction with the stakeholders, right? So we have done first stage of anaerobic digestion. मग मटेरियल बाहेर काढा, पुन्हा त्याच्यामध्ये कल्चर टाका, पुन्हा त्याला पॅक करा, आणि पहिले you keep it for 15 days, you pack it, you unpack it, put the culture, once again pack it, and wait for next 15 days. So we found that we require 30 days such that the carbon to nitrogen ratio from 55 it come to 15. And for that we require 30 days. Right? But then the paddy, the compost that we were getting has fibers and has a foul smell. एक दुर्गंध यायचा त्याचा. Then when we took this model to the industry who has funded entire project, they said that एकदा anaerobic digester मधनं काढून पुन्हा anaerobic digester मध्ये टाका. They appreciated की तुम्ही 90 दिवसाची प्रोसेस 30 दिवसावरती आणली. That's fine. पण म्हणे एकदा पॅडी बाहेर काढल्यानंतर पुन्हा पॅडी आत टाका, दॅट इज व्हेरी टीडियस अँड डिफिकल्ट टू डू. राईट? मग व्हॉट वी डीड इज दॅट वी फाउंड आउट की मला एकदा पॅडी काढून दुसऱ्यांदा का टाकावी लागते. वी फाउंड दॅट द pH of the entire mass was highly acidic. In acidic atmosphere, the microorganisms जे डिग्रेड करणारे आहेत, they were not working properly. आता आमच्यासमोर प्रश्न हा पडला की आता आम्ही याची pH मेंटेन कशी करायची की ती ऍसिडिक होऊ नये, so that the activity of microorganism doesn't die. Now we come up with we have now new challenge before us. We have two challenges. The two-step anaerobic digestion process, we want to make it one step. That is one. Second is that to make it one step, we want to maintain the pH inside the reactor. We come up, मी आता तुम्हाला गोष्टी स्वरूपात सांगतोय, पण it took lot of thinking. What we found is that the biomass ash, कोणतीही ऍश, कोल ऍश म्हणा, कोणतीही ऍश जी असते, राख जी असते, it is highly alkaline in nature. The pH of ash is somewhere 10 to 12. So what we did is that initially during the first phase of packing, we added ash along with the paddy straw, and we found that the decomposition, the longevity of microorganism has increased from 15 days to 21-22 days. The material used to work, the bioorganism, the microorganism used to work up to 20, 21 days, right? So we brought 30 days to 21 days with one step. But for that, we had to add ash. माझा प्रश्न पडला, ऍश असते का? क्षेत्रांना विचारलं, म्हणून आमच्याकडे ऍश असते म्हणे. काही नाही तर चुलीमध्ये असते. आम्हाला ऍश मिळणं हा काही मोठा प्रॉब्लेम नाही. So that means what we were thinking, that's available. So they said that in that area there are a lot many industries which uses rice straw, which uses sawdust as a fuel, right? And the ash which is coming out is a serious problem for the industry. They want to take care of the biomass ash which is produced, right? So that biomass ash, which is otherwise a waste for industry, has become one of the ingredient for the composting. Now the question is, मी जर कंपोस्ट मध्ये टाकली, will it enrich my compost? The answer is yes, because the biomass ash, as I told you, that it contains phosphorus, it contains potash, it contains so many micronutrients, right? So that we are now adding to compost. Compost has become enriched now. So this all we did in a reactor. I'll show you another video now. रिॲक्टर घेतलं, रिॲक्टर मध्ये सगळं पॅकिंग करायचं, सगळं ठरलं. मग प्रश्न हा पडला की शेतामध्ये कोण रिॲक्टर लावणार आहे? शेतामध्ये हे सगळं कसं काय केलं जाईल? तिथे रिॲक्टर लावा, तिथे रिॲक्टर मध्ये मिक्सिंग करा, हे तर शक्य नाहीये. आणि मोरेवर कंपोस्टिंग कसं केलं जातं? जेव्हा लोक शेण वापरतात, हे करतात, तेव्हा कंपोस्टिंग कसं करतात? मग बघितलं गड्डा करतात. मग आम्ही विचार केला, मग हे गड्ड्यामध्ये करता येईल का? पण ते चॅलेंज आहे. आणि पॅडी स्ट्रॉ हलकं आहे. एक तर पॅडी स्ट्रॉ हलकं आहे, दुसरं त्याच्यामध्ये आपल्याला पाणी टाकून जेव्हा मिक्स करायचं आहे, इट्स व्हेरी डिफिकल्ट टू मिक्स, बिकॉज इट्स द पॅडी has very fine one layer of silica and wax, and that makes the paddy surface water repellent. So mixing is a difficult charge. बाहेर मिक्स करायचं आणि मग ते त्याच्यामध्ये भरायचं. जेव्हा कंपोस्ट शेणाचं किंवा ओल्या कचऱ्याचं केलं जातं, इट्स हेवी, राईट? That's comparatively easy. Handling paddy straw is a very notorious biomass, and to handle it, it's very challenging. But then we come up with the pit model, right? Now I am going to show you the second video, right? And I'm going to show you two videos now. One is presentation, जे मी आता बोललेलो आहे ते 5 मिनिटांमध्ये सगळ्या गोष्टी सांगितल्यात. And then I will tell you the final model which has come up. And from 26th, so first model जे मी फायनल मॉडेल म्हणतोय ते लागलं 16 नोव्हेंबरला. 26 नोव्हेंबरला जस्ट 3 दिवसापूर्वी फायनल मॉडेल्स आलेले आहे की जे आता ऍक्च्युअल शेतामध्ये लागायला सुरुवात झालेली आहे. तुम्ही व्हिडिओ पहा, त्याच्यानंतर मी त्याच्याबद्दल सांगणार. मी विचार केला होता की आपण कोणती केस स्टडी घ्यायची. मग विचार केला की लेटेस्ट केस स्टडी आहे आणि सध्या आपण पॅडी आणि हे ते सगळं बघतोय आणि त्या गोष्टीच्या अनुषंगाने I thought that I should talk about a problem identification, the steps to follow, right? So let me take you to one presentation. It doesn't have a background music. Read it. This is the background. लोक जाळतात आहे, सगळ्या गोष्टी होतात आहे. गव्हर्नमेंटने काय म्हटलं 2019 recommendations. The best and the most environmentally suitable use of paddy straw is its incorporation in soil itself, on-farm utilization. And decentralized model. गावातल्या गावात शेतकरी स्वतः करू शकायला पाहिजे. So what we have done, we have come up with a culture which can digest it very fast. So it's a two-stage process, anaerobic followed by aerobic. Aerobic मध्ये सध्या फक्त उघडं करून ठेवून द्यायचं. We don't require any external energy. We don't do any chemical pre-treatment. We require minimum water and minimum volume of the reactor. So how the anaerobic digestion is carried out? Take PDC, which is a paddy digestion culture. Pulverize it, mix it with water of equal volume, 1:1 ratio. Add culture, add biomass ash, and you just pack it for 21 days. Open it and you do aerobic digestion. Aerobic digestion is known to farmers. It's very simple process. So trichoderma is used in second phase. This is the complete process flow diagram. The process flow diagram where you are using a reactor. This is not a farm model. This is the industry model. So Merino industry is partner. So we did a lot of pilot runs before we actually made it commercial. So now it's pre-commercial tests are done. This is now commercial. These are the reactors, the 7-meter cube reactor, and an aerobic phase for composting. This is the pit model, but we have modified the pit model. The quality of compost is all good as per the standard of FCO. This is what I was talking about. The cellulose content, and we have reduced the cellulose content to 6.82 from 45. Presently, what we are doing is, you will find that in the market, there is nothing called crop specific and soil specific compost. That is precisely what we are working. If you have cotton, we will give you cotton specific compost. If you are doing horticulture, there will be crop specific culture, right? Okay, fine. The final model which has come up after a lot of iteration is this layer model. This is in Hindi. You listen to this.
सबसे पहले 10 किलो राइस पैडी डालो आप और इसको लेवल करो आप। लेवल करने के बाद इसमें 5 लीटर कल्चर डालो आप। अब 5 लीटर कल्चर डालो, सही तरीके से डालना है, चारों तरफ का मिक्स करके। धीरे से कल्चर डालने के बाद 10 लीटर पानी डालिए आप इसमें। सही तरीके से डालना है, चारों तरफ डालना है। बराबर चारों तरफ डालना है। धीरे धीरे डालिए चारों तरफ।
See, 10 kg material, 10 kg paddy
पानी
straw,
डालने के बाद में आप इसमें 3 किलो बायो एश डालिए,
ash.
चारों तरफ करके डालना है। इसको अच्छे से मिक्स कीजिए आप दोनों हाथों से।
See, we tried to solve. This is the actual model which is going to be implemented, and instead of digging a dig, what we are doing is we have created
अच्छे से मिक्स करना है।
सुन लो पहले इसको।
अब 100 ml ट्राइकोडर्मा 1 लीटर पानी में ऐड करके डाल दीजिए।
Now they will do it. What has been done now? We in August we have come up with a pit model, but in the pit model, what we found is challenging is mixing outside one, and second is once we mix it, we will have to fill the pit. After 21 days, we'll have to take the entire compost out. That was ergonomically from farmers' ease point of view, it was not at all convenient. So this is a small structure on the floor has been created. This is created making use of urea bags. The urea bags are waste which are available abundantly with the farmers, right? The dimension is 1 meter by 1 meter and the depth is half a meter. It contains 70 kgs of paddy, and we call this, what you are seeing now, we call it as a layer or a biryani model, where अभी इन्होंने जो बताया कि you take 100 kgs, sorry 10 kgs of paddy, you add 5 kg of culture, you add 10 kg of water, you add 3 kg of biomass ash, then trichoderma, mix it. So that is layer 1. Then you'll have second layer, then you will have a third layer, right? And to pack one such bag, the reactor we call it as, takes just 30 minutes. It's extremely convenient for the farmers, right? They need not lift anything. So, and moreover, the time required has reduced drastically. It has now reached less than 30 days, right? So what we have done, we use very rich engineering understanding. We use the understanding of the anaerobic digestion, solid state fermentation. The amount of water required is minimum. Second, the volume of the reactor is minimum. The time required is minimum. And fourth is the ease of operation, something which the farmers can do on their own farm. Now, what we are now planning from today onward is that one such reactor, जो आता ते तुम्ही पाहता ते 1 meter by 1 meter and half meter, carries 70 kgs, right? And such 70 kgs, one paddy straw, 1 acre of land produces 2 tons of paddy, right? Now, what has to be done is I want to finish entire digestion in maximum 4 months. If it starts in the month of December, January, February, March, April, maximum up to April. Otherwise, once again, rain will start, right? This is once in a month activity the farmer has to do, and he will get extremely rich compost. Now, he can use this compost made from the paddy straw in the same field of paddy. Otherwise, generally the compost is made up from municipal solid waste or maybe kitchen waste, other agricultural waste, right? Now we are working along with IARI, Indian Agricultural Research Institute, PUSA, such that our hypothesis is if I make use of paddy-based compost in a paddy field, the activity will be synergic, right? I think this is almost done. They spray it, they pack it.
इसको दबाइए
Hmm.
मिक्स करने के बाद
Look at the ease of operation. 2 unskilled laborers are doing it.
दबाने के बाद में इसको आप बैच कंप्लीट हो गया है आपका और इसको आप ढक दीजिए
इसको ढक देंगे, उसको पैक कर देंगे, right? So let us come back to the presentation part. So we have validated, and now we are in a phase of dissemination. The industry has planned to produce 600 tons of compost in the this first financial year, जो अभी से start होने वाला है उसमें. Now let us find out, evaluate the solution. What have we done? Have we come up with a new procedure? Probably yes. There is an existing process of composting. Everybody knows it. What we have done differently is that we have come up with a culture that can accelerate the process. That is one. Second is that most of the composting processes, they either involve anaerobic or involve anaerobic. We have come up with a hybrid of this. We fused aerobic and anaerobic just because we wanted to reduce time and make it easy for the farmers. So existing process we have improved. The third thing that we are planning is we are trying to make crop specific and soil specific. The kind of soil that we have here in Nagpur, the kind of soil Delhi has, Punjab has, is totally different. So we are now interacting with the soil scientists. So in our group, we have soil scientists. We are making compost soil specific, right? So I thought that I should tell these points as well. The question is that from where the idea come, right? I always ask the students, what is the idea येईल कुठून? What's the source of ideas? And I will tell you my experiences. The source of idea is interaction with common people. One. And most important thing is that interaction with the people who do not have the same background that you have. If I'm a chemical engineer, I would prefer to interact with the people who are not chemical engineers. The work that we have done here, we have learned, I personally have learned a lot from a lot of biology. So I interacted with biotechnology, biochemistry people. I interacted with people from agronomy background. I interacted with people with soil sciences background. I could know that yes, there are so many types of soils. Then the most important thing is that I try to learn a lot of botany, how plant grows. And we found that innovation and the source of ideas lies at the interface of different disciplines. Interact with common people. Understand empathetically when we interact with them, we understand their problems. And when we feel the problem, with that sensitivity, we try to look for the solution. And most important thing is intuition. And for intuition, the meditation, prayer, that plays extremely vital role, right? So I stop here. And as I told you, it is a lot of discrete presentation, but that's fine. That is what I plan, right? So if you have any doubt, a query, I would welcome. But I think we have 5-7 minutes more. And If you have anything that I will try to address. And before that, I would like to share. Yeah. At the beginning, I had one question. At the end, also, I have one question. I would like to ask you the things that you learn from the presentation. Right? Saurabh, I'm done.
Thank you so much, sir, for sharing with us an excellent case study, which is in line with the subject, and we would be able to understand what are the different phases, how a particular problem is addressed, and how actions are taken. Thank you so much, sir.
Somebody has asked a question. What is the cost?
Yes, sir, please.
What is the cost of this process with respect to the traditional process? See, as far as the cost is concerned, the conventional compost is somewhere 4 to 6 rupees. This is also close to 4 to 5 rupees. But the value-added compost is what we are now doing, crop-specific and a soil-specific. That will be close to 12 to 40 rupees.
Okay. Is the cost.
Right? Okay. So, what problems do you face while taking process from lab scale to science scale? I think I answered this. Answered you when we what are the problems faced from pilot to. So how many problems were there? I think I answered during presentation. Achha, what happened to the biogas form? In case of solid state fermentation, we make sure that the culture that we are using, we are arresting the formation of biogas. The biogas formation is very less. That is almost negligible. What was the approach to model the kinetics of the reaction? I not understood the approach. We did the kinetic. What we have done, we have tried to study the variation of carbon to nitrogen ratio as a function of time. At a regular interval of time, we found out how cellulose and hemicellulose are changing. Well, for that, the easiest thing that we did is we try to find out the amount, the pH content and the VOC content. Can paddy straw be used as an alternative for furniture making instead of wood? Yes, there are a couple of startups where they are making use of paddy for your different utensils. It's there. You can search and you can find out the use of paddy straw for furniture and utensils. Does government provide subsidy for this? Government is providing subsidies for machines which can thrash, pulverize the paddy straw. But as far as our process is concerned, yesterday only there was a meeting with the officials in Niti Aayog. So we are looking for a subsidy. But right now, government has what pledged through Niti Aayog, what pledged through Agriculture Ministry, that they will help on-farm and decentralized models. So government is giving subsidy in terms of machinery, right? I think सर्व मी बऱ्याच प्रश्नांची उत्तरे दिली आहेत. If anybody has anything.
Quite a good amount of interest students are showing for this particular case study, sir, and it is actually inspiring. So we, as a follow-up activity, we are also working on purification of methane or storage of methane. One of my BTech students, we are into simulation of biogas that is generated, and what we are thinking of as of now is how to use, because biogas contains many other gases as well, which decreases the calorific value. So we are investigating that should we separate methane from biogas and then use it as a fuel, because it would increase the efficiency of burning as well, and also it will give more calorific value to the end consumer. So we are investigating as a follow-up activity to this. And I'm sure
In fact, people are using. There are typically instruments, and people are using these hollow fibers for separation of methane. There are things which are available. You can explore those things, Saurabh.
Okay. Thank you so much, sir.
Okay.
Thank you so much.
Thank you.
Sir, I'll just introduce you to our next speaker. He's Dr. Makaranda Pimpalpure. Sir, good morning.
Namaskar, sir.
Sir, you are on mute. Yes, sir.
Hello. Yeah.
So, Dr. Makarand Pimprapure, sir is an alumni of LIT itself, and he did his PhD from University of 20, and he's into giving consultancy in flow reactors. Sir, you'll be interested that he specializes in process intensification, flow reactors. Sir, I welcome you, and on behalf of LIT IIC,
Thank you.
I request you to please engage with our attendees. Thank you so much.
Sure. Thanks for a kind introduction. I think you need to enable. I'm unable to share my screen. So
Sir, can you now share your screen? You are again on mute, sir. Sir, we cannot hear you. You are on mute.
can you hear me now?
Yeah, we can hear you.
Let me share. Sorry. Can you see my screen?
Yes, we can see.
Good morning, everyone. Again, I'd like to thank you, LIT and IIC, for giving me this opportunity to make presentation on introduction to process intensification. So yeah, it is like honor and privilege to, get connect with all the students from LIT and faculty. Special thanks to Professor Mankar and Professor Banose, with whom I have been interacting for different forum. So today I'm going to talk about introduction to process intensification. So what I'm going to do, I'm going to briefly give my background in terms of what I have been doing, a little bit about my organization, the company which I have recently started. This is just to prove point that, I'm talking, all this talk is based on the experience I have spent in this area of process intensification. One additional point I would like to make is, I have been working in area of so-called process application engineering. That means how to implement these technologies at lab scale, at pilot scale, and production scale. So there are two aspects when you are doing those things. One is understanding the fundamentals, not really tweaking or trying to develop new technology, but understanding existing technology and how to make use of those. So that is a part of application engineering. So my talk will have a strong flavor of application engineering. That is by design, because that has been my experience, and I think that is the area of interest for coming days. So brief introduction about myself. So I have started this organization, MaxSpeed Technologies. It's quite a young organization. It's just 1 year old. My background is after my graduation from LIT. I have done my MTech from IIT Chennai, and I have done PhD from University of Twente. I have more than 20 years of experience. So most of my area of work had been process engineering, process intensification, reaction engineering, and flow chemistry. The earlier organization I have worked, is Corning, Dow Chemicals, GE Plastic. And after my graduation, I had a stint of working in Indorama at Butibori in the production plant. In terms of flow chemistry experience, as a part of my previous organization, I was helping them to set up a business of flow chemistry. So it involved a kind of handholding of the customer. So providing technical training, setting up a flow chemistry lab, designing dosing system for customer, providing techno-commercial evaluation of project, and of course, a very technical aspect of process optimization and defining a scale-up solution. Brief about MaxSpeed Technologies. So MaxSpeed Technologies is built upon core strength of chemical engineering and mechanical engineering. So as I explained, chemical engineering aspect is reaction engineering and process intensification. And mechanical engineering aspects are basically product design, modeling and simulation, and manufacturing capabilities of the equipment. What we offer, so MaxSpeed is offering can be seen as a 3-bucket. So first is a flow chemistry related product. So we have our own flow reactor which we have designed and which we are manufacturing. And these reactors come at lab scale, pilot scale, and production scale. So philosophy is based on our experience. We have developed some standard product, and because of our capability, since we are designing and manufacturing those, so based on the process requirement, we have capability to make appropriate changes in the design. Two other important components required for flow chemistry is dosing solutions. So we are in process of developing our own pumps and NRV. And another component for flow chemistry requirement is heating cooling circulators. Other things for as a part of MaxSpeed we are providing consultancy services, typically those to set up a flow chemistry laboratory, helping customer in improving batch processes or converting batch processes into continuous one, in terms of process development and finding scale-up solutions. Third component, what we are doing is we are providing a detailed commercial level of training on flow chemistry and CFD, computational fluid dynamics. So CFD training is done at our facility here at Pune, but because of Corona, that is kind of on hold for some time. And additionally, because of my interest in academia, I am also providing different trainings to different academic institutes. So key topics are process intensification and conceptual process design. This is just to give a snapshot of the reactor, what we provide. So we call it as a neutron series reactor. So it's a shell and tube kind of structure. And we have designed our own static mixer. So basically this reactor provide enhanced mixing and heat transfer performance. And all this has been done optimized through advanced CFD simulation. In terms of MOC, we are providing metallic, so it is SS and Hestoloi currently. And in terms of product, as I explained, lab scale product is a 10 ml, pilot scale reactor is 100 ml, and production scale reactor is 1 liter onward. So these are nominal volume, and based on the requirement, this volume could be tweaked. So it could be 5 or 15 ml, 50 or 150 ml, so on and so forth. Since these are metallic equipment, they can be operated up to high pressure. So currently, because of the requirement, we are providing them this reactor which can be operated up to 50 bar. But if required, these can be easily operated up to 100 bar. In terms of pressure, again, since these are MOC is metal, they can be operated in the temperature range of -60 degree to 300 degrees Celsius. In terms of interfaces, like in order to operate this reactor, these need to be connected to different pumping dosing system or pumps and heating cooling circulators. So we are providing a standard interface. So this can be connected with any those peripherals. So there is no limitation. So this is more or less about myself, my company, and the product what we are making. Now moving to the topic of today's discussion. Process intensification, introduction to process intensification. So what I'm going to do is I'm going to talk about a couple of definitions. So process intensification is a vast topic, and there are many popular areas of research and work which has a close connection with process intensification. So it is interesting, or it makes sense to look at the definition of each concept and try to understand how it is correlated with process intensification. Again, process intensification is based on the research area and the application area that has been defined in a many different ways. So also look at the definition of process intensification. Then I'm going to talk about fundamental views and elements of process intensification, how it is implemented, what are the different concepts. Then I'm going to talk about some specific examples of equipments, that is hardware, which are used for process intensification. So we are going to use this concept to understand what are the fundamental of process intensification and how they are correlated with other concepts. Then next two topics are quite close to my heart. So would like to talk or discuss about the challenges which is faced for process intensification. So here I'm going to talk from perspective of the technology developer. So basically you develop some concept of process intensification and then convert that concept into a workable model. So what are the different steps involved and what are the challenges in each step, that I'm going to talk. Then next topic is techno-commercial viability. So here the talk is more from the end user perspective. So as an end user, which you are not developing a technology, but you are evaluating certain technology and you want to use, what are the metrics, what are the criteria you are going to use. And then I'm going to again go back to the list of equipments, what we are going to see in process intensification first part, and we'll evaluate each equipment, how techno-commercial viability of those components could be evaluated. And I would conclude my talks in terms of what is a different area of work for in terms of process intensification and how they are related to each other. So yeah, I think I would be glad if my talk could motivate some of the students to take up process intensification as an area of study for further study or as a part of their career. Coming to definition of different concepts, so one of the keyword or buzzword these days is a green technology. So how green technology is defined, it is basically environmental, any technology which is environmentally friendly in production and supply chain. So that is a definition of green technology. And if you we'll see some definition of process technology. So some part of process technology and green technology, there is an overlap. Similarly, sustainability. So a simple definition of sustainability is meeting needs of present without compromising future needs. So again, this will involve conservation of energy, conservation of minimization of waste. So all those concepts is also relevant in case of process intensification. Then in academia as well as in industry, there are many groups or subgroups which typically works, and they call it as a novel technology group or emerging technology group. So typically novel or emerging technologies are the technologies which are which are in the developmental phase, or their development and application is largely unutilized. So which are kind of a novel. Next is in industry, there are many groups which are their objective is improving efficiencies or improvement in the process. So typically objective of those groups or those things are lowering, their objective is lowering of operation cost. So there are some overlap between these activities and what you try to achieve in terms of process intensification. Last but not least is a process system engineering. So basically process system engineering deals with the design and operation of complex production system by development and application of modeling and computational method to simulate, design, control and optimize process. So basically the simple way to understand process system engineering is basically when you're talking about a complex production plant, you can split it into a reactor part or a reactor system and then separation system. And traditionally, by fundamental engineering, chemical engineering principle, you can try to optimize your reactor system and you can try to optimize your separation system. But by design, like by operation, these two systems are like strongly interlinked. So process system engineering is try to reactor system and separation system such that the complete solution A plus B. So it's not optimization of A or optimization of B, but optimization of A plus B. Coming to definition of process. So, ability and base of the define process intensification slightly differently. The concept, or I would say main concept, but sometimes the fine details could be interesting to understand because it would be related to how this technology process intensification would be implemented. So first definition, it talks about a reduction in main plant item and installation cost. So here the author is more the commercial aspect of it, and then how to reduce those cost, either the actual capital cost or and then the installation cost, which is part of the capital cost. Next definition, it talks about strategy of reducing size of the chemical plant. But here the idea is to reduce the size of chemical plant, but for given production. So idea is not to reduce production. So if there is a specific production requirement, P kgs per hour or per annum, then idea is, can you produce same amount of material, but using relatively smaller size of the plant. Definition is kind of extension of this concept, where it is talking about decreasing of the equipment, decrease in the energy consumption, and decrease in the waste formation, and ultimately leading to a cheaper, safer, and sustainable technologies. Next concept talks about kind of enhanced integration, wherein multiple operation could be done using simple apparatus. Third is, I would say, a fundamental definition. So what it talks about radically innovative principles, or rather paradigm shift in process and equipment design, and which will benefit. And then this benefit could be in terms of increased efficiency, improved efficiency in capital utilization, and decrease in waste, and so on and so forth. Last definition, it talks about sustainability of profitability in presence of increasing uncertainties. So this is more this concept is more talks about the robustness of the solution and how it can sustain the uncertainties of the day-to-day operation. Next, I call it as a visual definition of process intensification. So process intensification, if you see, the crux of all definition is put together, would tell us that if you can reduce the equipment size by order of magnitude, that will enhance and it will lead to all the benefits what each different author is talking about. So left-hand side gives the snapshot of the existing chemical production facility, big towers, which could be a distillation or different operation. Right-hand side shows kind of a typically office space kind of an environment where you are building this plant. But the key to remember is the throughput or production of liters or tons of chemicals you are producing. In both picture, they are exactly same. Next is interesting to again try to understand comparison, similarities and differences between process intensification and process system engineering. So process system engineering basically aim is multi-scale integration of existing and new concept. And the focus or interdisciplinary kind of collaboration is limited. So typically they use various model software, numerical methods, just a lot of, I would say, mathematical modeling and simulation. And then interface between applied mathematics and informatics and chemistry is limited in this case. When you talk about process intensification fundamentally talks about a new concept and processing methods and equipments. Process intensification, mostly it's an experimental science. So of course, you need to do some modeling and simulation to develop concept, but proof, ultimately proof is experimental, and it involves a lot of experimental data generation. And here the interface between different disciplines is very strong. So chemistry, catalysis, applied physics, mechanical engineering, material science, electronics. So basically you are trying to use new concepts which are not really explored to date, or explored to a minimal level, and then explore those concepts and come up with the solution which is commercially viable. So in nutshell, basically process engineering, it talks about incremental change, whereas process intensification, it talks about paradigm shift. So again, that is the difference when I was talking about if there is a group in any industry or any research group which talks about process improvement. So many times their work would be around engineering, that is incremental change. In order to implement process intensification, that is a paradigm shift, there your fundamental definition of problem need to be appropriately done. Coming to next topic, that is elements of process intensification. So fundamentally, process intensification can be classified in terms of equipments and in terms of methods. And again, in terms of equipment, that can be classified as equipment for carrying out chemical reactions, and then equipment carrying out unit operations, so which does not involve chemical reaction. So some of the kind of well-known examples for equipment for carrying out chemical reaction is microreactors, which is well-known. Then monolithic reactors, static mixer reactor, spinning disk reactor. So we are going to see a bit more about microreactors kind of configuration and spinning disk reactor later on. In terms of equipment which does not involve chemical reaction, so compact heat exchanger, microchannel heat exchanger, so on and so forth. In terms of method, again, achieving process intensification by implementing different methods. So there are a list of methods which are mentioned here. So one is a multifunctional reactor. A reactive distillation is one of the most explored technology, I would say. And on the similar line, there are different type of reactor which can carry out unit operation as well as so reactor crystallization, reactive extraction, so on and so forth. In terms of hybrid separation, typically there is a use of membrane technology. So membrane technology, typically if it is integrated with absorption or distillation, those kind of the solution which lead to a hybrid separation. Next method is use of alternate technology. So use of microwave technology or UV radiation is quite common, but then you can also use solar energy, ultrasound, plasma technology, or electric field. Some of the other methods is use of supercritical fluid dynamics, so supercritical fluid. So in presence of supercritical fluid, there is an enhanced mixing, and then you can get an enhanced heat transfer, and then you are going to operate your processes in a totally different operating window. And then there is another concept that most of these operators reactor, they are operating under a steady state condition, but it is possible that you can operate this equipment under a dynamic or periodic operation, and then you can exploit some of the characteristics of process to get this advantage. So this is overall landscape of process intensification. What are the different equipments and methods we have seen? So moving forward, I'm going to talk about couple of examples, couple of equipment which is used for process intensification. We'll try to understand basic equipment, what are the principles involved. And later on, we are going to use this example from a developer perspective and end user's perspective. What are the challenges in terms of development of this technology, and for end user, how he will evaluate such technologies for implementation under commercial environment. So first equipment we are going to talk about is a plate and a frame type of heat exchanger. So as name suggests, left hand side what you can see is a structure of plate. So many plates they are bundled together, and then they are put on a frame, and that is why it is called plate and frame kind of heat exchanger. Right hand side shows kind of a schematics and a principle of use of a plate and heat exchanger. What you can see this blue arrows, that is a cold utility or a cold stream, and hot arrow is a hot utility. In a plate kind of heat exchanger, this hot and cold stream, they are passed through the alternate plate, and then heat transfer takes place through the face of this plate. So if you can see a closer look at the structure of this plate, so it has some sort of pattern. So this pattern enhances the surface area, and then they also avoid kind of short circuiting of the fluid. And then by use of this gasket, you can prevent or decide if certain fluid will pass on this face, or it will just move through this plate. So by arrangement of this gasket, you can decide a movement of this hot and cold fluid. So this is overall structure of this equipment, and the principle involved is basically the depth or the distance between two plates is very, very small. So one dimension is made extremely small. So that creates very high surface area per unit volume, and then that enhances the overall heat transfer of this equipment. So that's why these are really efficient equipment. And if in next picture, what you can see is comparison of a conventional equipment, conventional tube and shell heat exchanger versus a plate and frame type of heat exchanger. So key advantage of this technology, one is because of the size, there is an energy saving. There is a small footprint, so there is a saving in floor space as well. Two other key advantage compared to conventional equipment. One is a capacity adjustment. So what you can see on the right hand side is this equipment, once designed, you can decide the number of plates which are being used. So that will generate a different surface area for heat transfer. So by removing number of plates on this frame, you can adjust the capacity of the equipment. That kind of flexibility is not really possible in a conventional tube and shell kind of heat exchanger. Second advantage is ease of maintenance. So in industry, when you are carrying out this heat transfer operation, either utility or your process stream can have some solids, or not by design, accidentally they can accumulate some solid. And if such solids get accumulated on the process side, on tube side or shell side, cleaning becomes quite complicated. So for some design, cleaning may not be at all possible, or some cases it would be a really long operation where dismantling of equipment and cleaning could take days or weeks of time. Whereas in case of plate and frame kind of heat exchanger, as you can imagine, you can kind of dismantle or remove each plate simultaneously individually, and then you can clean the surface of each surface. So in terms of maintenance and then maintaining the efficiency of this equipment, it is relatively simple. So those are the key advantage for plate and frame heat exchanger. Next example is pervaporation membrane. So basically, pervaporation is a word which is combination of two words, permeation and then evaporation. So here principle, what I have shown left hand side schematics is this dark color is basically a membrane, and then there is when it comes in contact with saturated vapor, basically the material gets it will diffuse through this membrane, and then once it comes out of this membrane, this can be evaporated by application by maintaining lower pressure at this interface. So basically, principle involved is permeation through membrane by permeate, and then it is evaporated into vapor phase. And then basically heat of vaporization is dissipated from the feed. So then there is a decrease in temperature of the feed in this operation. So again, conceptually, there are two types of membrane which are possible: hydrophilic and organophilic. So hydrophilic is basically it permeate water preferentially, while as organophilic it permeate organic component preferentially. In terms of equipment, how to convert this concept into equipment. So this is a pervaporation membrane. What is being done is there is a feed to this equipment, and which is kind of continuously recirculated. During this recirculation, this permeate will permeate permeation of the preferential component, either water or organic material, will happen through the reactor through this membrane. And at the other end of this membrane, it is connected to vacuum pump to maintain to reduce the vapor pressure or reduce total pressure, and this will lead to evaporation of whatever things with evaporation of the permeate. And when this evaporated permeate moves forward, it is condensed and then it is connected. It is collected. So this is the overall operation using pervaporation membrane. So this pervaporation membrane can be used in as a hybrid distillation unit, hybrid distillation pervaporation operation. So idea is like you can convert azeotropic distillation. So alternative is use of hybrid distillation and pervaporation. So I'll briefly try to explain azeotropic distillation. So schematic is given on the right hand side. So ethanol and water, it is basically form the azeotrope. That means beyond certain composition, it will form a constant boiling solution, and you won't be able to separate ethanol and water after that. So typical methodology is you add entrainer inside that. So one of the most commonly used entrainer is benzene. So when ethanol and benzene is added together, basically it forms a heterophasic three-component azeotrope. So when this three-component azeotrope is taken from top of one of the from the top, basically it can be phase separated into two components, and then ethanol rich material can be feed back into ethanol column, and then water rich can be sent into another, and then you can remove the ethanol and water from this component. So some of the key problem with this this kind of unit operation, sorry. So a key disadvantage or problem with this kind of arrangement is, one is a designing challenge. So in order to design this kind of equipment, you need a lot of data. And again, troubleshooting of this equipment. So once you design, you are able to operate it under a steady state condition. If you face some problem, troubleshooting of this equipment becomes very challenging because it involves optimum operation of two distillation column and the other equipment. Plus, the capital cost of this technology is quite high. So it involves two distillation column and other peripherals. So alternative to that is given on the left-hand side. It's a distillation pervaporation. So what happens is you start with distillation operation, and then you remove the azeotropic solution from the top, and then this azeotropic solution is exposed to a pervaporation operation, wherein which lead to a further separation. So here 80% ethanol is taken from the top of this column, and then this 80% ethanol is concentrated in two steps using pervaporation to 95% and then 99.8%. And whatever water is removed from this operation is kind of fed back into the system with residual ethanol. And from this distillation column from the bottom, you can collect water. So this is a principle whereas pervaporation can be integrated with distillation to achieve efficient distillation for isotropic components. Next equipment is a spinning disk reactor. So here principle is basically so as name suggests, this disk is kind of rotated at extremely high high speed, which is of the order thousands of RPM. And because of that, it lead to intense shearing and mixing in the thin film. So it generates very thin film on the surface of the spinning disk, and then it has very intense shearing and mixing. And because of that, it lead to an extremely high heat transfer, mass transfer. So on the spinning disk, if you put two different reactants, so then they will spread out in a very thin film, and using because of that, it will generate high surface area per unit volume, and because of that high surface area, it will lead to a very high rate of reaction. And because of the surface area of the heat transfer will happen through the surface area of this disk, it will also maintain the isothermal condition. So basically, the residence time provided by this equipment is very, very less, is of the order 1 second or less than 1 second. And this is the overall structure of this equipment. So there is a spinning disk which is provided with the cooling arrangement. So the surface of the spinning disk is maintained at the desired temperature. And then there are feeds which are from this top, which comes on the top of this spinning disk, which will spread throughout, and then they will come down from the border of the spinning disk. And again, this complete chamber, is maintained at different at desired temperatures. So I'm sorry, I think I'm seeing my complete screen and there are some questions. So what I would do is I will take a question at the end of this presentation. This is the arrangement of spinning disk equipment. So this is a commercial reactor. So there are multiple spinning disks which are lying one above other. So as I explained, the residence time obtained for each chamber is very, very small. And if you add multiple chambers, then that is just to enhance the residence time, because based on the chemistry or kinetic requirement, you might need different residence time. And then this is right hand side is a total commercial setup. So in order to operate this spinning disk reactor, what you need is a dosing system to dose the chemicals appropriately at a desired flow rate. You need a heating cooling circulator just to maintain temperature. So this is just to give idea of the equipment. And typically this is suitable high intrinsic rate. For example, nitration, sulfonation, polymerization. So these are the examples which are available in the literature. Next technology to achieve process intensification is use of alternate energy source, so photochemistry. So in this case, UV radiation can be used to carry out reaction. So this is just, I'm giving one isomerization example which can be carried out using photochemistry. So right hand side, I'm giving typical schematics of the batch reactor. So what it consists of, in the center, there is a UV lamp which is enclosed in a chamber. And then this chamber is provided with a cooling jacket. So you can see water inlet and water outlet here. This is because typically this UV lamp also it heats up and radiates a lot of heat energy as well. And this life of this lamp can be affected if it kind of reaches very high temperature. So typically it is recommended that UV lamp it need to be maintained under cooled condition. And outside this this jacketed chamber, there is another chamber in which you can see the level of chemical. So basically UV radiation is coming from the inner chamber, and then they will dissipate from this interface. There is some sort of studding is provided at the bottom of the outer chamber, and then you can also carry out gas liquid experiment. So there is a gas inlet given here. So gas is bubbled from here. It provides some sort of agitation, and then heat source is provided from this. So this is typically a batch arrangement. Left hand side shows the continuous flow arrangement. So in this case, what you can see, a Teflon tube which is kind of found on the this kind of chamber. So there is a light source, UV source within a small jacketed chamber, and then what you can see here is an inlet and outlet for the coolant to pass through it. In this case, the concept here is this tube is continuously exposed to UV radiation, and then your feed can come from one end. It will move through this tube, and it can move out of the. So this is how continuous operation can be achieved. So here principle is basically energy source is UV. So just by maintaining UV source and sometimes temperature of the reaction mass, you can induce the reaction. And basically here the temperature of source, that is UV source and reaction mass, it's need to be controlled. So by maintaining these two concepts, you can carry out photochemistry in a batch mode or in continuous mode. This is just to show how the big equipment, this is just to give size of the, so this is a man standing inside this huge reactor, and this is overall schematic of the reactor. So this photoreactor, it could be very small, 1 or 2 liter, or in this case, it's very, very big. So here basically source of energy is a UV radiation, and it is UV source is maintained at constant temperature with this specialized design. So these are the jacketed temperature which are inserted along the periphery of this reactor. So this will ensure that UV radiation is kind of diffused uniformly throughout this chamber, and it is also maintained at low temperature. Again, inside the reactor, there are different design of baffles and agitators. So they are designed such a way so as to maintain constant agitation within the system, so that the complete reaction mass is exposed to UV radiation in a uniform manner. So this is the concept of photoreactor can be used for at the production scale. Next topic is basically microreactor technology. So sometimes it is also called as a flow chemistry. So this is a matrix of mass transfer and heat transfer. So on left hand corner, there lies a stirred tank reactor, which is one of the fundamental reactor to carry out chemistries. So there are well-known limitations for stirred tank reactor. It is in terms of mass transfer and heat transfer. And conceptually, different reactors are given in context with stirred tank reactor. So if there is an enhancement in mass transfer, those reactors will lie above on mass transfer matrix. And then if there is an enhancement of heat transfer in comparison with stirred tank reactor, those lies on the right hand side. So there are different configurations which are available. So enhancement of mass transfer, there is a jet injector, pulse column, static mixer, rotating pack bed. In terms of enhancement in heat transfer, there is a plate heat exchanger, what we have seen in earlier example, loop reactor, spinning disk reactor, static mixer, and plate heat exchanger, combination of that. And then on almost, I would say, right hand top corner is a microstructure reactor, which gives a very good mass transfer characteristic as well as a very good heat transfer characteristic. So basically, the principle here is by design itself, the reactor is designed such a way that it gives very high heat transfer as well as very high mass transfer. Some of the commercial equipment which are available in market. So one example is Corning. So Corning has their patented design, which is so-called heart shape structure. So using this heart shape structure, they have made this individual plates, and then these plates are connected in series so as to give certain volume of the reactor. In case of MaxSpeed, we have shell and tube kind of a structure, and then inside tube we have our own static mixer design, which is a proprietary design. We are not sharing details about those. Basically, in a microreactor, you can achieve the manifestation is different. So this is a plate and frame kind of structure, whereas this is a shell and tube kind of structure. And then in terms of design, there is an enhancement in the heat transfer area, in the enhancement of mixing by some sort of inserts on the process side. In terms of MOC, reactor comes in a MOC of glass and ceramic, whereas we are providing metallic options, SS and Hestoller. So after seeing different equipment which are used for process intensification, now I would like to come to a topic of challenges. So when a designer is designing these technologies or this equipment, what are the challenges faced by designer? What are the steps taken by how to convert from concept to a workable model? So first example, I would like to talk about a flow chemistry, which we have just seen here. So first step would be definitely design of a microchannel. So in order to achieve process intensification, so key is microchannel design, because channel itself is providing mixing and heat transfer. Then next is converting this microchannel into the reactor design. So in case of Corning, we have seen that this so-called heart is converted. We at MaxSpeed, we have used shell and tube configuration. Next aspect of this equipment is application engineering. So once reactor is ready, somebody would like to use those reactor for carrying out chemistry. Then ease of operation becomes important criteria, because you should be able to easily use those equipment. If the operation becomes complicated or difficult, then that is one of the big challenge. Next is a choice of peripherals. So this equipment, most of these components, you're talking about equipment used for in chemical industry, they need some sort of fluid transfer. So typical peripherals would include pumps. It will include heating, cooling, utility circulation within that. So how easy it is to integrate this equipment with peripherals is very important aspects or criteria. Next aspect for challenge for converting this concept to workable model is scalability. Because like if you which are kind of appreciated, but the problem with those concepts is those are kind of a lab activities. Because of the fundamental design or different issues, those could not be scalable. So scalability is very important. So you should have a solution which can be operated at lab scale, pilot scale, as well as production scale. So anything which cannot be scaled up from lab to production, it could be interesting from learning perspective, but it will have a limited impact on industry. Next concept is transferability of solution. So if you're talking about a flow chemistry solution, so idea is whether this is a equipment which can handle or which can solve a specific solution. So for example, it says that this is an equipment which is done for nitration. But then the question is whether the equipment which is designed for nitration, can it be used for hydrogenation or oxidation with minimal changes. So here I have given example, anything which is done for exothermic reaction, can it be used for non-exothermic, or anything which is done for miscible system can be used for immiscible liquid-liquid or gas-liquid system. Next is again, in addition to related to transferability is how you are placing this equipment in market. So are you making it as a tool, R&D tool, or you are trying to sell it as a solution for specific chemistry? Next important is ease of transfer of know-how on equipment operation. So for example, if you are developing your own equipment, probably because of lot of exposure, all the people who are involved in project can easily handle those equipment because of lot of training. But once you transfer that equipment at customer end, you need to train those people. So the training required in order to operate those equipment is very, very high, or it is very complex, or you need extremely specialized skill in order to operate those equipment. Then that could be a biggest challenge. Of course, there are cases where you need a specialized skill. For example, if you're talking about analytical equipment like NMR, you need a special skill. So here I'm not talking about that. A reactor is meant for to be used by all chemists and all chemical engineers. So idea is any given equipment can be used by any random qualified chemist or chemical engineer with minimal training. Next, I'm going to talk about the challenges in converting concept to workable model for membrane technology. So first challenge would be to come up with a theoretical design of membrane. What is a pore size? What is a MOC? So as we have seen that there is a hydrophilic and organophilic membranes. So each MOC would be different, and based on the molecular sizes of water and organic moieties, the pore size could be different. Next would be manufacturing of the membrane. How one is concept, you know that based on concept it can be done, but how well you can manufacture that, and what is the reproducibility of that. Next challenge would be again converting those membranes in a workable or usable equipment. Again here other concepts or challenges are similar to microreactor or flow chemistry. One is integration of it with peripherals, different pumps or heating cooling circulator. Scalability of solution, lab pilot production. Again, transferability of solution. So here the question is like if you have a membrane with a hydrophilic membrane. So if you have developed a solution to separate methanol and water, so whether it can be done for all alcohol or it can be implemented for all water organic components, so on and so forth. Similarly, sale of equipment as a tool versus a solution for specific chemistry. So whether you're selling it as a membrane technology to take care of process involving alcohol, so on and so forth. And similarly, ease of transfer of know-how on equipment operation to customer. So these are the aspects from the developer technology development perspective. Now I would like to talk about from perspective of the end user. So end user, if he faced with any problem, then he need to evaluate different technology to solve his problem, and then he need to evaluate techno-commercial viability of specific process intensification technologies. So sometimes the target could be to compare two different process intensification technologies and try to choose one of them. So matrix to evaluate potential PI technologies. Again, as we have seen, process intensification technologies can be split into two based upon the maturity. So one is some process intensification technology which are in the early stages of adaptation, and some which are a bit popular, which are in the late stage of adaptation. So something which is in early stage of adaptation, typical thing to check is trends in academic publications. So because of most of new technologies is coming from the fundamental which are developed by academia. So what are those trends, and what is the level of publications? Again, related to the quality of publication from the group which are making those publications. Next would be number of various group working and continuity of work. So many times, like if you take the newest buzzword, so if you look for nanotechnology, you will find many people who are working in nanotechnology. So That also indicates the popularity of the topic, number of groups working. But most important to check is also continuity of work. So many times there is a buzz and people start working for 1 or 2 couple of years. There are some PhDs or publications from that, and after some time that group stops working in that area, probably because there is no light at the end of tunnel. So probably they have hit some wall, and then they know probably those cannot be really exploited for commercial application. So that is something that need to be checked. Next important aspect is patenting. So this in academia, and many professors, they come up with their own startup, and before doing that they typically patent that technology. So if some technologies are patented, that means it has some commercial values. That also indicates that probably commercially this technology is good. As I was mentioning, again, next is startup coming from university. So based on experience, people can have that feeling whether certain technology can be implemented. Then publish example of pilot and production. So most of the academic publication, they are based on the data done at a lab scale. But then there is a trend wherein people try to share the example of pilot or production. If not in publication, it would be in different different events, different workshop, or trade shows, and so on and so forth. So that need to be checked. And most importantly, transferability of technology. So if all the publication is simple example is separation of water and methanol, and you are talking about the separation of ethanol. So fundamentally, you really need to check that if it is transferable from what is available in the literature versus what is your problem. In terms of late stage of technology adaptation, typically a key thing to check is what is the technology support for evaluation and adaptation. So there may be, again, if there is some technology which is in a late stage of technology, you are likely to try it on the different problem which has not yet been solved. So in that case, you need to generate more data than what is available with the technology provider or in literature. So in this case, support provided by the technology provider in generation of data becomes important. Next is successful example. What are the technical and commercial installation for specific technology by that particular vendor? Confidence on return on investment. So if any technology is in the late state of technology, so all the costings are very transparent. You are aware of the different components required to implement. So capital cost is quite clear. And based on the data generated, you can get some sense of operation cost. And then return of investment can be done with more confidence if technology is in a late stage of adoption. And last but not least is the investment capability. So there could be technology which is perfect kind of match for the problem you are facing, but that cost of technology is much higher than what you can spend. Typically, there is a mismatch. So with this background, now let us go back to the example what we have seen, and then try to evaluate based on the matrix we have seen. So for example, if you want to evaluate plate and frame heat exchanger, so we can say that plate and heat exchanger with a very quick Google search, you can say that it is a established technology because there are multiple vendors which are providing this kind of technology. So in order to implement this technology, key thing to check is what is the initial investment and what is the operation cost, that is a return on investment. Then specific points you need to evaluate for this is what is the performance versus expectation, what is a footprint reduction, last but not least, what is a transferability in short term and long term. So many times what happens is you would like to implement certain technology to solve one specific problem. So you might want to use plate and frame heat exchanger to solve because for some process that is the best fit. But another strategy, you say that you are using hundreds of shell and tube heat exchanger, and then in some future plan is to replace each of them with plate and frame heat exchanger because of the advantage. So the strategy when you want to use this equipment to solve one specific problem one time could be different against when you want to adopt this technology in large scale in your organization and kind of do revamping of the overall technology what you are using. Again, hybrid distillation per evaporation. Again, this is also established technology. There is a rich literature available. Here again, you should be able to have return of investment calculation, initial investment and operation cost. Again, related to specific points for this example would be performance. The most important would be membrane life and cost. So if you take a look at this setup, so the key thing which is making this whole equipment possible is the membrane. So membrane performance and life is very, very important. So so for example, there are two scenarios. Membrane is very cheap and you need to change it frequently. So cost of changing is not very high, then that is acceptable solution. But if membrane is cheap and cost of changing is very high because of the shutdown and all, then it is not viable solution. Another extreme is changing membrane is very easy, not very costly affair, but the cost of membrane is very, very high. Then in such scenario, there is always a risk. So what is a warranty or guarantee if there is a frequency in the failure of membrane? So all those aspects need to be understood, accounted when you are doing return on investment. Next is spin disk technology. Again, if then your conclusion would be spin disk. It seems to be a niche technology. This is usable for very specific application only. So this cannot be used widely. So in that sense, a number of applications which are available in literature are also limited. Again, here a return of investment calculation is must, initial investment and operation cost. Specific point in addition to performance here would be scalable solution. So spin disk reaction by principle, you understand that there is a mechanical component. So there is a mechanical motor which spins this reactor rigorously. So when you are increasing the dimension of this disk, the mechanical component required would be very different. And what is the life of those mechanical equipment? What is the maintenance cost? What is the confidence and support, warranty, guarantee? All those aspects need to be considered when you are when you decided to go ahead with this kind of solutions. Next is again photoreactor. So similarly, photoreactor is a niche technology. Again, can be used application. Return on investment is a key thing where you should be guess about cost as well as operation cost. Again, in order to, in addition to performance, what is the maintenance cost, or in this case, the key component is your what is the life of light source, what is the frequency of change, what is a guarantee, warranty, evaluated. Last but not least, again, a scalable. So as I have shown that there are some solutions which are available in large scale, but then before operating that, you would be generating data in lab scale. So whether this lab scale data is kind of scalable, or there is a scalability issue or scalability factor you need to consider. All those things need to be understood, and accordingly final decision need to be made. In terms of microreactor technology or flow chemistry, again, this technology is in early phase of adaptation in pharma, fine and specialty chemical. Again, in order to invest in it, you need to have initial investment and return on investment calculation done. So some specific requirement here is performance, scalability of solution. But most importantly, if you look at this equipment, it consists of three components. First component is basically reactor, which is a static, it is a non-moving part. Second component is dosing pumps, And third component is heating cooling circulator. So heating cooling circulator per se is also a very stable, robust solution. The key here is dosing pumps. So choice of dosing pumps, how to select appropriate dosing pumps, how to maintain. So skills on peripherals becomes essential for success of flow chemistry. I have seen many instances where people have purchased very expensive flow reactors, but they were unable to manage the peripherals, and that lead to a lot of delay in getting a successful data from their equipment. This is my take on kind of what is a knowledge and business change of process intensification. So what are the key stakeholders? What are their briefly, how in a one word, how would you describe their role and responsibility, and how they are connected with each other? So first step for process intensification is a researcher or academician. Here, the objective or the contribution of this researcher would be to find out or principle which can be used for process intensification, and then using that principle make a working element. Then the design role of design engineer is start with the working element and convert it into the working equipment. Role of application engineer is to use this equipment for the intended purpose. So, for example, use reactor to carry out chemistry, or use equipment to carry out separation operation. And then once this technology is available, the last but not the least, or the key component of this chain is a technology adopter. So the end user or the investor. So role of investor is to invest in this new technology and then make a commercial benefit out of this equipment or technology. So if there is no buyer, basically all this earlier may not be useful. So typical money is flowing from technology adopter, reverse way. In terms of feedback, basically at each level there could be a feedback loop. So there of course is a feed forward loop, because a researcher need to explain design engineer the basic things what he is doing, so and so forth. But the feedback loop is also important, because this is to take care of practical aspects. So basically the working element could be very good based on the principle, but to convert that into working equipment, probably there could be trade-off, or there need to be some tweaks that need to be done. So there is a feedback loop from design engineer to researcher. Similarly, there could be a feedback from application engineer to design engineer or researcher. Similarly, technology adopter. So that feedback from technology adopter again can go to application engineer or design engineer. So the key probably focus for technology adopter would be overall cost and efficiency, commercial aspect of that. So this is more or less the knowledge or business chain of process intensification. And in order to be successful, basically each component on this chain, they need to do their part. And for chemical engineers or for student, I mean, from career perspective, they can look at each component, and that could be the area of expertise for them. Or if they are interested, probably they can move along the chain and then at some point try to stabilize, or be a owner of company which will take care of all those components. So I think that is more or less what I wanted to explain from a process intensification perspective. So thank you for your attention. I'm open for questions now. So what I'll do is I'll stop sharing. I think it will make easy for me to read the comments and respond to questions. If somebody likes, I think they can also ask. So I'm not sure if people are allowed.
Sir, I had one question.
Yes.
For a particular volume, suppose if you are considering a reactor, and for a particular volume there is some space that is required. Typically,
I think your voice is a bit breaking. Could you repeat?
Hello. Yeah. Sir, for a particular reactor volume, there is some space that is required on field, right? And now we have to replace that reactor with a more intensified reactor. Typically, what is the area that increases or decreases? Because what we do is we convert that volume into smaller volumes, number of smaller volumes, and then we do the reaction in that particular volume. So, does the area enhancement is there, but in space of in terms of the space that it gets, what is the effect? And second is for these technologies, there must be a very high pressure drop which all these reactors have to come across. So how to deal with this? Because certain reactions may not be favorable at higher pressures. So in this case, what is the approach?
Okay, so I think to your first question, it is a little bit more practical, and I mean there is no very specific answer. So there is a decrease in footprint when you go from conventional reactor to kind of a intensified reactor. So the motivation from end user could be 2-3 ways. So one could be many times what you need to see it is as a replacement of conventional reactor when there is an expansion. So it is less likely that it's a well-established plant because there is already capital cost has been spent. So the existing working reactor, nobody is going to replace that with the smaller reactor because he has already made that capital. So it will happen when there is a expansion plan. So the advantage for customer is that when he expand that, so for new plant, the total floor space required would be less compared to the existing. And many times what happens is these reactor, they are efficient. So in this is less compared to the existing equipment. So many times one of the motivation to adopt new technology is to reduce the waste, because now there are the norms from pollution control are quite stringent. So there is a limitation in terms of amount of waste can be generated for a specific site. And if they are almost at the brink of that, and with that limitation, if they want to expand, so in that case, it makes sense to use this new technology instead of conventional technology. Answering your question, basically, that is one of the challenge you're talking about. Is it okay? Like first answer, I think I answered your first question.
Yes, yeah.
Answering your second question, so basically when you are doing particularly for a reactor, there are three aspects. One is a heat transfer, mass transfer, and pressure drop. So there is always some compromise. So based on each, if for example, if I'm developing my reactor based on my experience, based on the data I know or I can collate from literature, I can decide the window. So there is always a trade-off, basically that has been the challenge. So most of the equipment, flow chemistry equipment which are available in market, there is a trade-off, and they have come up with some compromise where their heat transfer and mass transfer may not be as high as the micro reactor. So they are mesoscale, but it is sufficiently high to achieve better performance than a conventional reactor, but still a pressure drop is minimal. So it is manageable. So typically most of this equipment, the pressure drop could be in the range of 4-5 bar, and getting dosing or pumping solution with that pressure, with those pressure range is available. So it is not a problem.
Sure. Thank you, sir.
I'll read out the questions and try to answer them. So first question is, what is the cost of this process with respect to traditional process? So basically the data for complete conventional process versus complete intensified, most of that involves a lot of proprietary information. So it is less likely that you will get those details. But this is a right question, or this is a question for application engineer or the technology adopter. So based on the data available, he need to do those paper calculation, and then based on those calculation, he can decide whether this whether new technology make commercial sense or not. Question are from earlier. I think 29. What kind of flow is is spinning disk reactor useful for high viscous reactant? Yes. So spinning disk has been used for polymerization kind of reaction. So because of very high shear, there is a shear thinning and high viscosity reactants can be done. But I won't be able to give you specific number as such because personally I have not worked on those technology. But in principle, spinning disk reactor can be useful for high viscosity reactants. What kind of flow is present? So basically most of the modern flow reactor, they are come up with some sort of static mixer. So you cannot use the conventional methodology of characterizing them like a different dimensionless number because of the internal structure. So most of the modern design, they are done using computational fluid dynamics. And there you have freedom to do calculation of heat transfer, mass transfer, without kind of calculating the dimensionless number. So per se, the velocity of the flow inside the reactor, so those kind of information may not be that important because that will get calculated indirectly in your during your calculations. Will process intensification be able to withstand increasing demand? So very interesting question. So I would say you can take it as a question or you can take it as a challenge. So idea is, can we keep on producing same amount of material or we can keep on increasing throughput by either decreasing or keeping energy constant and waste constant. So I would say it is a sustainability or climate change challenge, because the idea for challenge for climate change is we need to continue to use same amount of fuels or energy without adversely impacting the climate. So I would say that this question is on the similar line. So I think it, as a chemical engineer community, I think we can take it as a challenge and make it possible. Is it possible to carry out high pressure process? So again, definition of high process could vary. So sometimes like 10 bar could be high or sometimes 1000 bar could be high. So most of this flow technology currently are being implemented in a pharma environment and fine and specialty chemicals. So there up to 10 bar or 20 bar is sufficient. But easily some of the metallic equivalent can be operated at a 100 bar pressure. So up to 100 bar, that is, I think it's relatively easy, straightforward or simple. But thousands of bar, I have not come across any solution. I mean, any process or solution for that. Yeah, second question is related to membrane separation, sustainability or implementation of membrane separation at a high volume. So I would come back with that. Probably I need to study a bit more on that. So as I explained, these membrane technologies, they are quite popular these days. I think the biggest use is also in terms of water purification. So I don't know the upper limit in terms of volume. Probably I try to check and share those numbers. But I think there is no limit for membrane technology. It is kind of improving day by day. I don't know the current numbers in terms of maximum volume it can handle.
If anyone has got any questions, you can unmute themselves and ask, sir. If you have got any specific question for which you require a very detailed answer or any very specific question, you please forward it to me. I will share the same with Pimpapure sir. Sir, thank you so much.
Thanks.
I hope your talk gives inspiration to our students and faculty members to start their journey in process intensification. and hopefully get something worthwhile in this field.
Sure.
So there is a question, as you mentioned that in previous diagram of traditional industry and intensified industry, they have same production. In that case, time required will be more for same production.
Yeah, so there are, I mean, if you talk about time, that is, I think, very interesting and insightful question. So when you talk about time, there are two times. So, or processing time and what is a total production time. So, for example, if you take process intensification, there are example where 10 kiloliter of batch reactor is kind of replaced by a 5 liter of intensified reactor. What it changes is the amount of time spent by material inside the for processing. So residence time for conventional reactor could be like a 2 hours to 10 hours, and intensified reactor it could be 2 minutes or less than 2 minutes. But if you see per day production, it would be of same order of magnitude. So it could be couple of tons per day. So basically, time spent by material inside the reactor is reduced, but the total production per day of that material it remains the same.
Right, sir. Thank you so much for accepting our invitation, sir. And we hope to have more such interactions with you. Thank you so much.
Sure. Yeah, and again, I will repeat. So if you have any question, feel free to forward it to Pradeep sir, and he, or like if you want to have one-to-one discussion or some specific thing, feel free to connect with me. I'll be more than glad to have more discussion. Thanks a lot.
Thank you so much. Thank you.